This is the third video in a three-part video series over the topic of volumes of solids and volumes of revolution by disks and washers. This is the second video over the volume of revolution by disks and washers and is an optional video for my students to watch. In this video, we're going to look at a couple of problems without being told what kind of volume of revolution it is. In other words, you won't be told whether this is a straight volume of revolution and you should use a disk, or whether this is a volume of revolution with an inner radius that is carving out a hole and an outer radius providing the outer surface of the solid. You'll have to revolve it and graph it in order to know. Let's take a look at this example, which is example 8 in our notes. Find the volume of revolution for the region bounded by the square root of x and y equal x squared about the x-axis. When we graph y equal the square root of x, pictured here with the black curve, and y equal x squared, pictured here with the green curve, we can see that there is a region that is trapped between the two curves, which here is shaded in purple. We want to revolve around the x-axis, so put a curving arrow to indicate this is your axis of revolution. Does the strips that you will draw, does each one touch the axis of revolution? The answer is no. In fact, the only part that definitely touches is the part at the very beginning on the far left lower edge of the picture. In this case, since we want to revolve around the x-axis, we draw our strips perpendicular to the x-axis by making them vertical. That means that our axis is going to be the x-axis and our differential is going to be dx, since the short end of the rectangles is dx. Now our inner radius is given by the distance from the axis of revolution or rotation, the x-axis, up to the closest end of each thin rectangle or strip. This is given by the y value on the green curve, which is y equal x squared. That means that our inner radius over here will be given by the value of r inner equal to x squared. The outer radius, on the other hand, is given by the distance between the axis of revolution and the far end of the thin rectangular strip. In this case, this is given by the y value on the curve, the square root of x, so that r outer is equal to the square root of x. When we're looking at these, then, we need to compute the volume of revolution by subtracting the inner radius volume out of the outer radius volume. Our formula, of course, is the integral from a to b of pi r squared with the differential, in our case dx, since the narrow end of each thin strip is dx. We will need to do this from x equals 0 to whatever the coordinate is here where they touch. To find out where they intersect, you will take each curve and set them equal to each other to find the intersection points. When you do that, you end up with the equation the square root of x equal to x squared. To eliminate the square root, you need to square both sides of the equation. To square both sides of the equation, you end up with x equal x to the fourth. Do not divide by x or you will lose one of the solutions. Instead, move everything to one side of the equation with 0 on the other and solve. This means that you will need to factor out the x, and this gives you x minus x cubed minus 1 equals 0. X cubed minus 1 does factor as x minus 1, the binomial, times the trinomial x squared plus x plus 1. This has two solutions, x equals 0 and x equal 1 from the monomial factor x and from the binomial factor x minus 1, giving the solution x equal 1. The trinomial x squared plus x plus 1 has no real solution, though it does have complex imaginary solutions. We take these two x-coordinates to become the limits of our integration from x equals 0 to x equals 1. Then we will have pi as a constant factor, and we multiply the outer radius squared minus the inner radius squared. Our outer radius is the square root of x, but don't forget that the formula is pi r squared, so we have to square it. Then we subtract the inner radius, which is x squared, and again, even though it already has a square, the formula is r squared, and r is x squared, so we have x squared squared. This becomes the formula for the volume of integration. Pause the video here and work out the calculus and see if you get the same result that I do. After squaring the square root, we end up with simply x. Squaring x squared gives us x to the fourth. This becomes a simple integration, and the result is 3 pi divided by 10. Let's look at our next example, example 9, from this section of the textbook. Find the volume of revolution for the region bounded by the square root of x again and y equal x squared again, but this time about the y-axis. This means that we're going to be rotating around the vertical axis, so draw your curving arrow to indicate that the axis of revolution is now the y-axis. That means that our inner radius goes from the axis of revolution to the closest end of the strip. Because our axis of revolution is vertical, our strips or thin rectangles must run horizontally. The narrow end of each of these rectangles is in the vertical direction, which means the differential is dy. Now what we will do is we will set up our inner as being the distance from the axis of revolution to the closest end of the strip. This is going to be the x value on this curve. In other words, r sub I is equal to the x value on the curve, the square root of x. Now this is going to be a bit of a problem because our equation is solved for y and not for x. You'll see in a moment what we have to do to switch this around. The short answer, of course, is take this equation and solve it for x. For our outer, we will need to go from the axis of revolution here to the farthest end of the strip, which is out here. This gives us our outer. In this case, we can see that our outer is in fact the x value on the other curve, which is y equal x squared. We can then solve this equation for x to get the x value on this curve. Let's take a moment now to do that work. Solving this equation for x, we need to square both sides, which gives me that x is equal to y squared. In solving the second equation, I need to take the square root, which normally would give me a plus or a minus. But notice that on this one, I am only looking at the right arm, not the left arm. The right arm is the positive arm. This tells me that x is equal to the positive square root of y, because I have the right arm of the parabola. That's what gives me the plus sign. Now what I can do is I can replace the x on this curve with y squared, so that our inner becomes y squared, and our outer becomes the square root of y. Now I need to figure out what the limits of integration will be. Remember that we go from where they intersect to where they intersect. In this particular case, what we need to figure out is where these two curves cross each other. The points of intersection are where we set them equal. However, from our previous work, we know that they're equal when x equals 0 and x equals 1. However, in this problem, the differential is dy, so we don't need the x coordinates, we need the y coordinates. In other words, what is the y value here when x equals 0 and when x equals 1? We can plug into either equation since these are the points of intersection to get the results. The square root of 0 is 0, so that point is the origin. The square root of 1 is 1, so this point is 1, 1. Notice you would have gotten the same values had you used y equal x squared. This means that our limits of integration are going to run from y equals 0 to y equal 1. They have to match the differential dy. So make sure that you understand that even though both x and y have the same value here, that's a fluke because of the particular function we're looking at. Now let's set up our limits of integration inside the integral so we can compute the answer. We're integrating from y equals 0 to y equal 1. When we look at our region, notice that the inner radius does not touch the axis of revolution anywhere but at the bottom left corner. That means that we need to compute the inner volume and subtract it from the outer volume. We can then compute this as the following: pi as a constant multiplied by the outer radius, which we have as, of course, the square root of y in terms of y. So we write the square root of y quantity squared for the pi r squared minus, now let's write the inner radius and square it. The inner radius is y squared. Therefore, we'll write y squared quantity squared. This is r, and we need to square it. Once we're done with this, we need to put on the differential, which of course in this case is dy, since the short end was in the vertical or y direction. Pause the video here and work out the calculus, then turn the video back on to see if your result matches mine. When we square the square root of y, we get y. When we square y squared, we get y to the fourth. This becomes a simple integral to evaluate. Don't forget to plug in the limits of integration, which are y values. Again, we got 3 pi divided by 10. Why did we get the same result? We saw previously that typically when you revolve about a different axis of revolution, your shape and your volume are completely different. Why not in this particular case? That is not really a normal result. Normally we get a totally different shape and a totally different volume. However, it happened here because the region is symmetric across the identity function y equal x. That happened because the positive square root of x and the graph of x squared only from x greater than 0 are true one-to-one inverses of each other. That is, they line up across that identity function, and they form exact mirror images of each other across that line. Therefore, when we rotate around the x or the y, we get the same shape. Thus, we get the same volume. This, however, is not the normal case, so don't expect this to happen unless your graphs are one-to-one inverses of one another across the identity function. This is the end of this video, just giving mixed practice on volumes of revolution by disks and washers. In the next video, we'll take a look at a different method of computing volume called volumes of revolution by shells.